Okay, so today our class is, we have a new lecture which is about frequency modulation, and this is in chapter 5 of our textbook, which is the Frenzel book. So it's fundamentals of frequency modulation. Main sections in this chapter: basic principles of frequency modulation and principle of phase modulation, phase modulation index and sidebands. So these three topics we discussed today, and the other two, noise suppression and frequency modulation compared to amplitude modulation, we discuss next week. Okay, let's see what is frequency modulation. I believe most of you understand what is frequency modulation. So, in fact, what we had in amplitude modulation, the amplitude of your carrier changes by amplitude of the message signal. In frequency modulation, the amplitude of carrier remain constant, but the frequency changes. So frequency go higher and reduce, changes high and low, depend on the amplitude of the message. So there is no change here for the carrier amplitude, it's just constant, but frequency keep changing. And that mainly depend on the amplitude of our voice or our message. So when the amplitude increasing, then frequency changes as well, maybe can be increased. In fact, you can design your carrier follow the amplitude direction. For example, if your amplitude increase, your frequency can be increased as well. When the amplitude decrease, frequency decreases as well. It can be other way around as well. You may design your system when amplitude increase, frequency decrease. When amplitude decrease, frequency increase. So in either case is possible, but one of them, of course, is you have to select as a designer. If you are a designer of frequency modulating system, so that is the two options. When there is no modulating signal, your carrier just oscillate in the based on center frequency. Sometimes it's called as resting frequency. So there is no increase, there is no decrease. It just remain as original or center frequency of your carrier. We have two terms. One is frequency deviation, is shown by FD. This is the amount of change in carrier frequency produced by the modulating signal. So this means the maximum and minimum frequency change in our carrier. So, of course, is not infinity, it is a range. Usually the systems designed to limit them It can be open for any value, but that frequency deviation is based on the modulating signal. So there is a maximum and minimum frequency change in the carrier. We also have the frequency deviation rate. So it means how many times per second the carrier frequency deviates above or below the center frequency. So this frequency deviation rate is, in fact, comes from the modulating signal. So the modulating signal is the one determine what is this frequency deviation rate. For example, if a modulating signal is 500 hertz, let's say sine wave. So sine wave, of course, then the frequency is fixed, so 500 hertz. Then the carrier frequency shifts above and below the center frequency 500 times per second as well. So maybe this figure helps to understand better. So the top figure is carrier. It's shown in triangle form for just better understanding. So the carrier is, of course, you can see amplitude is constant. Frequency also is constant. That frequency is our carrier central frequency or center frequency. And the second figure, which is a red sine wave, is our, let's say, message signal. So the message signal amplitude is increasing, then decreasing. So when this is changed, let's see what happened to our modulating signal, modulated signal or the carrier. If you look at the beginning part, initial part, where my mouse is, there is no signal. So you can see same carrier in the modulated signal as well. As soon as your sine wave started or your modulating signal started, so then you can see your frequency is increasing. At the peak, you look at the peak part, then there is more dense wave, means the frequency is increased. So we have frequency increased. So then the sine wave amplitude is decreasing, going to the negative side. We can see the density of your wave is reduced, and this shows frequency of your modulated signal is less, means lower frequency. If you follow, you can see those parts where the modulating signal going to the peak amplitude, your frequency at the modulated signal is the highest, and at the minimum peak of your modulating signal, the frequency of modulated signal is the minimum. So that is how your frequency modulation works. So the rate of this change in the frequency or frequency deviation rate, of course, depend on how quickly your modulating signal changes. But the change of your frequency in the carrier or in the modulated signal, all is depend on the amplitude. So we have one example. Assume a carrier frequency of 150 megahertz. So this 150 megahertz is our center frequency for the carrier. If the peak amplitude of the modulating signal causes a maximum frequency shift of 30 kilohertz, so depend on how big is the amplitude of our modulating signal, we assume there is 30 kilohertz shift in our carrier frequency. Then the carrier frequency will deviate up to 150 megahertz plus 30 kilohertz. So if you convert 30 kilohertz to megahertz, will be 0.03, which is you can see here. So we have 150.03 megahertz going upward, and again it go down with another 30 kilohertz, so become 149.97 megahertz. That is the range of carrier frequency changes. So the total frequency deviation is the higher frequency minus the lower frequency range become 60 kilohertz, which is 2 times of the maximum shift in your modulating signal. So then we can say that the frequency deviation for the 150 megahertz carrier frequency is plus minus 30 kilohertz. So means our center frequency go maximum of plus minus 30 kilohertz, changes or varies by this range. So that is how our carrier frequency changes based on modulating signal amplitude. So let's have one more example. A transmitter operates on a frequency of 915 megahertz. The maximum FM deviation is plus minus 12.5 kilohertz. So means this FM goes maximum and minimum range of 12.5 kilohertz variation. What are the maximum and minimum frequencies that occur during modulation? So that is quite straightforward. So we have 915 megahertz. We can convert this to kilohertz to be easier to combine with our deviation range. So we have 915,000 kilohertz. So the maximum deviation is 915,000 plus 12.5, and the minimum deviation is 915,000 minus 12.5. This is our maximum and minimum deviation. So one more time, note that the frequency of the modulating signal has no effect on the amount of deviation. So no matter what is the frequency of your modulating signal, so the amount of deviation is strictly a function of amplitude of the modulating signal. So only the amplitude of our modulating signal effect on the carrier deviation. What we've seen in previous example was a form of analog modulating signal, but if your modulating signal is digital, so means there are limited number of amplitude change, like what we have in this example is like a binary. There are only two levels of amplitudes. There is a low voltage and high voltage. We have 0 volts and 3 volts, for example, and these keep changing. There is no any other amplitude here. So therefore, what you have is only two frequencies, because frequency modulation is supposed to change based on the amplitude. So now you have, let's say, 0 volts. It has one frequency. When it shifts to higher voltage in your message signal, the frequency changes to another frequency, but remains there because your amplitude is constant. So therefore, if you look at here, you have only two frequencies. So this is, we call it frequency shift keying. So which is used in transmission of binary data in digital cell phone and low speed computer modems. We can use this for, of course, more than two levels. Here we have two levels because it is binary. You may have other numbers of level, maybe MRA, for example, they have more than two levels, maybe they have four levels. So frequency shift keying can be used for those as well. So then they have four different frequencies. So of course, frequency changes by the level. So while the level voltage is fixed in your message signal, frequency remain same. So the change of frequency happened at this transition. So the rate of change here, how quickly this change, the frequency in your carrier changes. So when this is, okay, this is phase modulation. So similar to what we talk about frequency modulation, phase modulation also is very similar to frequency modulation, but here, when the amplitude of your modulating signal changes, we change the phase of the carrier. Instead of changing the frequency of the carrier, the phase of the carrier changes. For example, for a sine wave modulating signal, so our modulating signal, let's say, is a pure sine wave. As the modulating signal goes positive, going towards, is in the positive, going towards the peak, means increasing, then the amount of phase, for example, lagging, means phase shifted, or your carrier lags the center carrier or center frequency. Then when your carrier lags the center frequency, we have our frequency reduced. So when the modulating signal goes negative towards the minimum side, then the phase shift become leading, means your carrier leading the center frequency, and then the carrier frequency increases. So of course it can be vice versa, but this is just one example. Here I am showing you same example we seen in figure 5.1. We have a carrier frequency, carrier signal, which has a fixed frequency and of course phase. So our modulating signal is a sine wave. Frequency modulation, we have seen how it change. When the amplitude goes towards peak, frequency keep increasing, and the highest frequency is at the center. Phase modulation is changing the phase. They look quite similar with frequency modulation. I mean, the wave, if you look, you may not easily understand, is this a frequency modulation or phase modulation, especially if your signal is analog. So, but they have some differences. We can see maybe if this is not very clear, we can see a little bit later. So if you look at the first part, when there is no message signal, you have just carrier frequency, there is no change. Then when your modulating signal started, you can see there are some changes in your modulated signal. When the signal going towards peak, there is some changes in your carrier. You can see here. Then when it's going down towards the negative part, there is a change in the amplitude. You can see your carrier also change. Here what we see, it looks like the frequency has been changed. So means it becomes more dense. When it goes towards the peak, it becomes less dense when it's going towards the negative side. So means your carrier, in this case of example, when it's going towards the peak, when the amplitude increasing, it become more dense, means looks higher frequency. When it is going towards the negative side, in your modulating signal, your carrier reducing the frequency. So in fact, this is mainly change the phase, but what we can see is the frequency change. Because when phase change, your carrier either leads the carrier frequency or lags the carrier frequency. So this leading and lagging also is like a change in the frequency. Here is a little bit maybe better to understand. We have this wave. It was a saw wave, but the peak and the minimum part has been cut, is clipped. So what we can see here, maybe a little bit better to understand phase modulation. When there is no signal, the carrier remain the same. Here it is shown, for example, frequency is increasing when your amplitude is increasing, and frequency is decreasing when our amplitude is decreasing. So the maximum frequency deviation produced by a phase modulator occurs during the time that the modulating signal is changing at its most rapid rate. So means the maximum change in the phase happen when there is the most rapid change in your modulating signal. So this is more visible when we show in the binary signals or digital signals. So you have your carrier frequency. Of course, the frequency across the whole modulated signal is constant. When the amplitude change, there is a sudden change in your amplitude, so you have sudden change in your phase. So this is when there is for digital signal, but when it's analog signal, you don't have a sudden change in your amplitude, so it's a gradually change. So you have your phase slightly change, not that rapidly. Okay, so if we look at the relationship between modulating signal and carrier deviation between phase and frequency modulation, so here we have in both FM and PM, the frequency deviation is directly proportional to the amplitude of the modulating signal. In phase modulation, the maximum amount of leading or lagging phase shift occurs at the peak amplitudes of the modulating signal. In phase modulation, the carrier deviation is proportional to both the modulating frequency and the amplitude. So this is the main difference between phase and frequency modulation. In frequency modulation, only the amplitude of the modulating signal affects frequency of your carrier. There is no effect from the frequency of your modulating signal. But in phase, both of them affecting. So here is showing two graphs which helps better understand what I stated here. So when this is the x-axis showing modulating signal amplitude, and the y-axis is frequency deviation, which is FD. When the signal amplitude increases, frequency also increases. This is the same for both PM and FM. Means carrier frequency changes by amplitude of modulating signal. Now you look at the second graph in the right side, or graph B. The x-axis is modulating signal frequency, which is FM, and the y-axis is frequency deviation again. If you look at here, for FM, the frequency remains constant when the frequency of the modulating signal changes. However, the PM, you can see the frequency also changes based on the frequency of the modulating signal. So means both amplitude and frequency of modulating signal affect on the frequency deviation of phase modulation. But for FM, is only depend on the amplitude of the modulating signal. So sometimes we convert PM into FM. So in order to make PM compatible with FM, the deviation produced by frequency variation in the modulating signal must be compensated. So means we need to remove those effects from PM, then PM becomes same as FM. This compensation can be accomplished by passing the modulating signal through a low-pass filter. So if you send your modulating signal through a low-pass filter, high frequency variation in your modulating signal will be attenuated or will be disappeared. So then the FM and PM modulation become quite similar. This low-pass filter is called frequency correcting network or pre-distorter or 1/f filter, and causes the higher modulating frequencies to be attenuated. So the FM produced by a phase modulator is called indirect FM. Similar to frequency shifting, we also have phase shifting. So the process of phase modulating a carrier with binary data is phase shifting, or we call it binary phase shifting or BPSK. So, but in general, we just call it PSK. So here we have a binary signal. Of course, binary signals have two levels, 0 and 1, or low and high. Here we have 0 volt and 3 volts. So you can see the phase has been changed when the amplitude of your binary signal is changing. So you have a like sine wave here. When it comes to the transition part from low voltage going to the high voltage, your modulating signal, there is a sudden change of 180 degrees in your phase. So your carrier change the phase and then continue going on with the same frequency and phase until it reaches to the next transition. There is another 180 degree phase shift. So this phase shift here is 180 degree, but other modulating signals, they have more than 2 levels. We can have more number of phase shift. And other than BPSK, we have QPSK, means there are 4 levels of phase change. We have more than QPSK as well. We have like 16 PSK or others, which the phase can be changed more than 4 different phases. In fact, PSK is very popular in advanced modulation to have many levels. They also combine with ASK to produce very high efficient modulating signals. Now we want to talk about the modulation index and sidebands. So we have seen the sidebands in amplitude modulation. We said we have double sidebands, single sidebands. That means something related to the frequency of your modulated signal. So when a constant frequency sine wave modulates a carrier, produces 2 sidebands. In FM and PM, same as in AM, side frequencies are the sum and difference of the carrier and the modulating signal. Other than this, in FM and PM, we have other pairs of upper and lower sidebands. Means there are more than one pairs. So in AM, we have only one pair, upper sideband and lower sideband. But in AM and PM, we have more than that. So that's why FM and PM have wider bandwidth compared to amplitude modulation. That is usually, but of course it's possible to eliminate them or filter those and make them something similar to AM spectrum as well. So here is one example. So you have a carrier at the center. So then you have your sidebands, upper sidebands and lower sidebands for example, an FM, for a FM modulated signal. You can see there are multiple of those sidebands. Here is showing the relationship of these sidebands with the carrier. So you can see FC plus FM. So the FM, let's say, is our modulating signal frequency. You have one sideband, which is carrier plus the FM. Second sideband is FC plus 2FM. Third sideband is FC plus 3FM, and so on. And in amplitude modulation, we have seen when we use binary signals which have multiple of harmonics of the fundamental frequency, the sidebands amplitude or the harmonics keep reducing when it goes to the higher harmonics or higher frequencies. In FM, this is not the case. You can see there is suddenly in some sidebands, the amplitude is higher than the previous amplitude. Here, for example, you have lower amplitude. The second sideband is less amplitude. The first sideband, third one is still decreasing. Then fourth one is increasing. So there is no a uniform condition here to say, okay, the sidebands amplitude reducing or the carrier frequency maybe remain constant, higher than the sidebands. This is not really valid for FM signal. There are different parameters affect on this sidebands amplitude and of course and also the carrier amplitude. We will see this a little bit later. Okay, so now we talk about modulation index. In amplitude modulation, we also had modulation index. So here we also have modulation index. The ratio of the frequency deviation to the modulating frequency is known as the modulation index, shown by MF equal to FD, which is frequency deviation, over FM, which is modulating frequency. So for example, if the maximum frequency deviation of the carrier is plus minus 12 kilohertz and the maximum modulating frequency is 2.5 kilohertz, modulating index is 12 over 2.5, so we have 4.8 modulation index. Of course, it doesn't have unit, it's unitless. In most communication systems using FM, maximum limits are put on both the frequency deviation and the modulating frequency. So means we limit both of them. So for example, in a standard FM broadcasting, the maximum allowed frequency deviation is 75 kilohertz, and the maximum allowed modulating frequency is 15 kilohertz. So in this case, our modulation index is 75 over 15 is 5. So as we shown here. So that is to make your modulation index fixed, and we know what is our maximum frequency of modulating signal and maximum variation of or deviation of your carrier. So let's have one example. What is the deviation ratio of TV sound if the maximum deviation is 25 kilohertz and the maximum modulating frequency is 15 kilohertz? Your carrier deviation is 25 kilohertz and the modulating frequency is 15 kilohertz. So our modulating index is 25 over 15. So we have 1.667 as our modulating index. So there is one more example. So what is the maximum modulating frequency that can be used to achieve a modulation index of 2.2 with a deviation of 7.48 kilohertz? Okay, so we have our deviation range, frequency deviation range of carrier is 7.48, and our modulation index is 2.2. So 7,480 hertz divided by 2.2, we have 3,400 hertz or 3.4 kilohertz. This is the maximum frequency of our modulating signal. So if you put a low pass filter, for example, for our modulating signal and adjust this to 3.4 kilohertz, then your modulating signal only have this range, just as example. Okay, so here I want to discuss about the Bessel functions. Giving the modulation index, the number and amplitudes of the significant sidebands can be determined by solving the basic equation of an FM signal. So this is FM general equation. So you have carrier frequency, amplitude, sine, which is your carrier, 2 pi FCT, which is here still is your carrier frequency. So the frequency changes with MF sine 2 pi FMT. Here we are assuming our modulating signal is a sine wave, and it could be something else. So solving this equation, or in general, when your amplitude of your modulating signal change, the frequency of your carrier will be changed. So to understand about those sidebands, the amplitude of the sidebands and frequency of them, so we need to calculate this. This is done by Bessel functions. I will show you after this. This is after solving this modulating signal with Bessel function is this form. So what you have is, we have your carrier, you have your sidebands now. So upper sideband, lower sideband for the first sideband, second sideband, third sideband, fourth sideband, and so on. So here I identified for you. So here is our carrier signal with the amplitude of J0 here. This is our first sideband. This is upper sideband and lower sideband. So your carrier frequency plus your modulating signal, and this is for upper sideband, higher frequency. This is for lower sideband. They have amplitude of J1. So this is the first sideband elements. For second sideband's elements, they have amplitude of J2, and the carrier frequency now is plus 2 times your modulating signal frequency, and another one for lower sideband is omega C minus 2 times of the modulating signal frequency. So, and so on. You have for multiple of them, and the amplitude keep changing. We cannot say the amplitude of the sidebands keep reducing. We are not very sure for FM. So is a little bit not uniform. So then this JNs, or these J's you see here, J0, J1, J2, J3, J4, need to be calculated using this equation, which is related to your modulation index. So after we calculating this, we know those Jn in this equation. In practice, you do not have to know or calculate these coefficients, since tables given them are widely available. So here is the table of Bessel function. Here in the first column showing your modulation index. So your modulation index keep increasing from 0 going higher value. Then second column is your carrier. So then the other columns shows the sidebands. Here the carrier means the amplitude of your carrier, which is in fact J0. So in this equation here, J0 is in fact this. Here it shows by carrier. Then first, second, third, fourth, and so on. These are the sidebands which represent J1, J2, J3. So means this is the first sideband, J2 is the second sideband, J3 is the third sideband, and so on. So when we want to calculate FM to know what is the sideband amplitude or the bandwidth, we need to refer to this table. Note that some of the carrier and sideband amplitudes have negative signs. So you look at here, for example, so they are negative even in the carrier or sidebands. So this means that the signal represented by that amplitude is simply shifted in phase by 180 degrees. So we also have amplitudes which suddenly change. For example, you look at here, for a modulation index of 5, you have your first sideband is negative, second sideband is 0.05, then third sideband is 0.36 increase, fourth sideband is, fourth sideband is 0.39, so then again is reducing. So that is something which they are not keep increasing or decreasing. And you can see some parts are just put a dash, there is no data, or the data doesn't show. Any sideband with a relative carrier amplitude of less than 1% has been eliminated. So when the value become very small, 1% compared to the relative to the carrier amplitude, they didn't show. The reason is when we talk about the the bandwidth of your FM, the amplitude of the sidebands are important, means how much power available in your sidebands. If the amplitude is too small, means there is no much power and it is not very significant in your demodulation. So there is no much power there, so you can reduce your bandwidth to collect only those sidebands which have or carry highest power in the sidebands. This Bessel function also can be shown in this form. This is showing the different sidebands. So this is related to the carrier, which is J0. This is for the first sideband, second sideband, third sidebands. So this is the value of the Jn, and this is the modulation index. So if you want to use this instead of table, you need to find the value by yourself. For example, you look at your modulation index, let's say 5. So then you need to search in this modulation index, what is your carrier amplitude? So here you can see it is negative minus 0. Let's say 1 something. You can see here 0.18 is your carrier amplitude, is negative for modulation index 5. Here you can see this is somewhere here. So then for the first sideband, you can find this is minus 0.3, something like 0.33 or 32. And if you look at here, it is the first sideband has an amplitude of 0.33. The second sideband J2, if you follow, is here when the for modulation index of 5, this is around somewhere positive, very small value of positive, less than 0.1. So if you look at here, you can see this is positive 0.05. And third one, we expect to be positive 0.36. Let's see that one. So you can see sideband J3 or third one for modulation index of 5 is somewhere here, which is, as we just now said, is about 0.36 is here. So that is, if you want to use the Bessel function in the graph, this is what you need to find by yourself. If you want to use the table, is a little bit easier. Okay, here I am showing you the sidebands and the carriers for few different modulation index. So let's say the first image or graph showing you modulation index of 0. No modulation or sidebands, it's just the carrier. So it means there is no modulating signal. So you can see there is no sidebands because there is no modulation signal. It's just the carrier. The unmodulated carrier in this has a relative amplitude of 1 with no modulation. All the power is in the carrier. So means this is the highest power which is in the carrier now. So let's go to another example. So modulation index of 1. So modulation index of 1, here modulation index, this is 1. So we should have carrier power 0.77. We have 3 sidebands 0.44, 0.11, and 0.02. Remember these sidebands, we have upper and lower sidebands. If you look at in these equations, when you have positive part of sidebands, negative sidebands also available. Upper and lower sidebands means for each amplitude of your sidebands, there are 2 copies. One is in positive, another in negative. So let's see here. So this is our carrier amplitude 0.77. You have 3 sidebands in positive and 3 sidebands in negative. So we have upper sideband and lower sideband. Of course, the amplitude of each pair are the same, 0.44, 0.11, and 0.02. The rest have lower power in the sidebands, doesn't show. And this is the bandwidth you need for this modulation index. So to receive all the power. But if you don't need the power of, let's say, 0.02, you can adjust your bandwidth to a smaller range. So with modulation, the carrier amplitude decreases while the amplitudes of the various sidebands increases. So means in our first example, there was no sideband. All the power is in the carrier. But when you have the sidebands, the power of the carrier reduced, while we have power in the other sidebands. So here is another example. Modulation index is 2. So we go to the table, modulation index of 2. Then the carrier amplitude is 0.22. We have 4 significant sidebands. The first one has amplitude of 0.58. Second one is 0.35. Third one is 0.13. Fourth one is 0.03. So let's see in our graph. So this is the carrier power, sidebands power. We have 4 sidebands as we've seen in the table. First one has the highest power, 0.58. Second one is 0.35. Third sideband is 0.13, and the last one is 0.03. The rest, if they are less than 0.01%. That's why they are not shown here. So if you look at here, the bandwidth of this modulation index is more than the bandwidth of previous example. Here we had only 3 sidebands, so means this is 3 times the frequency, the maximum frequency of modulating signal, but here you have up to 4 times your modulating frequency. There is one more example, which is having only 1 sideband. The rest is not shown. And this one we call it narrowband FM, but let's see what is narrowband FM first. So narrowband FM is any FM system in which the modulation index is less than pi/2, means 1.57, or your modulation index is smaller than pi/2. This is a special case of FM in which the modulation process produces only a single pair of significant sidebands like those produced by AM. So to make your FM to have similar bandwidth as AM, we do this rule, means we eliminate higher bands and only let the bands, the first, in fact, side bands to be passed. The rest will be eliminated. Narrowband FM is widely used in communication. It conserves a spectrum space at the expense of the signal to noise ratio. So means we reduce the bandwidth, but we need to increase the power. So when you reduce the bandwidth, what you lost is your power. So in other words, it spends more power but utilizes a smaller bandwidth. So this is the one example. So the modulation index of 0.25. So let's see in table modulation index of 0.25. It has only one sidebands of 0.12. So the carrier has a power of 0.98. So this is the carrier power and this is the sideband power. So if you don't have enough power, here the bandwidth is smaller. If you don't have enough power, you need to increase the power to achieve enough signal to noise ratio. So this was few examples of FM with different modulation index. Okay, so I have one example here. State the amplitudes of the carrier and the first 4 sidebands of an FM signal with a modulation index of 4. So use figure 5.8 or 5.9, the two Bessel functions we shown either the table or the graph. We need to find a state the amplitude of the carrier and first 4 sidebands of FM signal with modulation index of 4. So when we have modulation index of 4, so this is modulation index of 4, the carrier amplitude is minus 0.4, and the first 4 sidebands are 0.07, minus 0.07, 0.36, 0.43, and number 4 is 0.28. So this is what we have here, which we can find from the table.